Hello everyone, I am going to present a PPT on digital system design. First, we are going to see is multiplexer and demultiplexer. Its aim is to design and implement the multiplexer and demultiplexer using logic gates and study of IC 74150 and IC 74154. Here the apparatus required is 2 3 input AND gate, 1 OR gate, 1 NOT gate, 1 IC trainer kit and patch cards as required. First, what is meant by multiplexer? A multiplexer means transmitting a large number of information units over a smaller number of channels or lines. A digital multiplexer is a combinational circuit that selects binary information from one of many input lines and directs it to a single output line. The selection of a particular input line is controlled by a set of selection lines. Normally, there are two n input lines and n selection lines whose bit combination determine which input is selected. This is the block diagram for multiplexer, and here's the circuit diagram for multiplexer. This is the truth table. Next, we'll see the simulation for multiplexer. We need 2 toggle switches, 2 NOT gate, 4 clock pulse, 4 NAND gate, 3 OR gate and 1 bulb. We'll give the circuit connections. Next, we are changing the 2 input NAND gate to 3 input NAND gate. Next, we'll give the input to check the output. We are naming bulb as Y output. Next, we'll see demultiplexer. Demultiplexer is nothing but it is a function of demultiplexer is in contrast to multiplexer function. It takes information from one line and distributes to a given number of output lines. For this reason, the demultiplexer is also known as data distributor. Decoder can also be used as demultiplexer. In the 1:4 demultiplexer circuit, the data input line goes to all of the AND gates. The data select lines enable only one gate at a time, and the data on the data input line will pass through the selected gate to the associated data output line. This is the block diagram for the demultiplexer. Here's a logic diagram and truth table. Next, we'll see the stimulation for the demultiplexer. Here we need 2 toggle switch, 2 NOT gate, 1 clock and 4 AND gates. Next, we label them. We'll give the circuit connections. Next, we'll give the inputs to see the output. Next, we'll see flip-flops. There are 4 types of flip-flops: RS flip-flop, D flip-flop, JK and T flip-flop. Its aim is to verify the characteristic table of RS, JK and D flip-flops. Here the apparatus required is 1 digital IC trainer kit, 1 D flip-flop, 1 JK flip-flop, 1 NAND gate and connecting wires as required. Here RS flip-flop, they are nothing but the clocked RS flip-flop. It consists of NAND gates and the output changes its state with respect to the input on application of clock pulse. When the clock pulse is high, the S and R inputs reach the second level NAND gates in their complementary form. The flip-flop is reset when the R input is high and S input is low. The flip-flop is set when the S input is high and R input is low. When both the inputs are high, the output is in indeterminate form. This is the logic symbol for the RS flip-flop. Here's the circuit diagram and the characteristic table. Next, we'll see the stimulation for the RS flip-flop. For that, we need 2 toggle switch, 1 clock, 1 SR flip-flop and 2 bulb. We are giving the connections. We are labeling them. Next, we are giving the inputs to check the output. Next, we'll see D flip-flop. To eliminate the undesirable condition of indeterminate state in the SR flip-flop, when both inputs are high at the same time, in the D flop, the inputs are never made equal at the same time. This is obtained by making the two input complement of each other. Here's the symbol for the D flip-flop. The pin diagram and the characteristic table is given. Next, we'll see the stimulation for the D flip-flop. We need two toggle switch, one clock, one D flip-flop, one AND gate, one push button and one NOT gate. We are giving the connections. Next, we are giving the inputs to check the outputs. Next, we'll see JK flip-flop. The indeterminate state in the SR flip-flop is defined in the JK flip-flop. JK input behave like S and R inputs to set and reset the flip-flop. The output Q is AND with K input and the clock pulse. Similarly, the output Q is AND with J input and the clock pulse. When the clock pulse is 0, both the AND gates are disabled and the Q and Q dash output retain their previous values. When the clock pulse is high, the J and K inputs reach the NOR gates. When both the inputs are high, the output toggle continuously. This is called race around condition and this must be avoided. Here's the symbol for the JK flip-flop. Here's the pin diagram and the characteristic table is also given. Next, we'll see the stimulation part for JK flip-flop. For JK flip-flop, we need two toggle switch, one clock pulse, one JK flip-flop and two bulbs. We are giving the connections. We are giving the inputs to check the outputs. Next we are going to see is T flip-flop. T flip-flop is much simpler version of the JK flip-flop. The state of the flip-flop is changed by a momentary change in the input signal. This momentary change is known as trigger and the transition it causes is set to triggering the flip-flop. Pulses trigger clock the flip-flops. A pulse starts from the initial value of 0 goes monetarily to 1 and after a short while returns to its initial 0 value. The clock pulse is either positive or negative. This is the symbol and the circuit diagram for the T flip-flop. Here's the characteristic table. Next, we'll see the stimulation for the T flip-flop. We need two toggle switches, one AND gate, one clock, one push button, one NOT gate, and one T flip-flop and two bulbs. We are giving the circuit connections. We are labeling them. Here the output is Q and Q bar for us. Next, we'll give the inputs to check the outputs. Next, we'll see serial in, parallel out, and parallel in, parallel out. Its aim is to study and implement the shift register in various modes of operation. First one we are going to see is SIPO, that is serial in, parallel out, and PIPO as parallel in, parallel out. Here the apparatus required is 2 D flip-flop, 1 OR gate, 1 isotrainer kit, and patch cords as required. Shift register is another type of sequential logic circuit that is used for the storage or transfer of data in the form of binary numbers and then shifts the data out once every clock cycle, hence the name shift register. It basically consists of several single bit D-type data latches, one for each bit 0 or 1 connected together in a serial or a daisy chain arrangement so that the output from one data latch becomes the input of the next latch and so on. The data bits may be fed in or out of the register serially, that is, one after the other from either the left or the right direction or in parallel, that is, all together. Next, serial in to parallel out. The register is loaded with the serial data, one bit at a time, with the storage data being available in parallel form. This is the pin diagram for serial in and parallel out. Next, this is the logic diagram. Here's the truth table. Next, we'll see the stimulation for serial in and parallel out. We need 4 D flip-flop, one toggle switch, one clock, one push button, one NOT gate, and 4 bulb. Next, circuit connections are given and input is given to check the output. Next, we are going to see is parallel in, parallel out. The parallel data is loaded into the register simultaneously and is shifted out of the register serially, one bit at a time under clock control. Next, here's the diagram for the parallel in and parallel out. Next, we'll see the stimulation for parallel in and parallel out. Here also we need 4 D flip-flop. One clock, one toggle switch, one push button, and one NOT gate. Circuit connections are given. and we are labeled also. Here the inputs are given to check the output. Next we are going to see is Ring and Johnson counters. A counter is a device which stores the number of times a particular event or process has occurred, often in relationship to a clock signal. They can count specific event happening in the circuit. Counters are broadly divided into two categories: asynchronous counter and synchronous counters. Synchronous counters, it has two types: ring counter and Johnson counter. Johnson counter, they are nothing but twisted ring counter. Next, ring counter. Ring counter is almost same as the shift counter. The only change is that the output of the last flip-flop is connected to the input of the first flip-flop. In case of ring counter, but in case of shift registers, it is taken as the output. Number of states in ring counter is equal to number of flip-flops used. For designing 4-bit ring counter, we need 4 flip-flop, and this is the circuit diagram for the ring counter. Next, input variables are RST and clock. X is equal to clock can be either a positive edge or a negative edge. The output variables here are Q0, Q1, Q2 and Q3. Truth table is also given. Next, we'll see the stimulation for the ring counter. We need 4 D flip-flops, 4 bulbs, 1 NOT gate, 1 AND gate, 1 toggle switch, 1 clock and push button. Next, we are labeling the outputs and inputs. Circuit connections are also given. Next, we'll see the stimulation. The circuit connections are given and inputs and outputs are being labeled. Here the inputs are given to check the outputs. Next we'll see Johnson counters. They are nothing but twisted ring counter. The alternative name of the twisted type is switch tail or walking Johnson type counter. The complemented output of ending flip-flop is feedback to the input of the starting flip-flop, where the stream of ones and zeros flow in ring form. The twisted type counter uses two control signals like clock and ORI, where clock and ORI are common to all four flip-flops. This is the block diagram for the Johnson. Here the input variables are RST and CL clock. If n number of flip-flops are used, then 2n number of states is required. Here the output variables are Q0, Q1, Q2 and Q3. Truth table is also given. Next we'll see the simulation for the Johnson counter. Four D flip-flops are given. We are labeling them. We are giving the inputs to check the output. Next, we're going to see VHDL program for half adder. Its aim is to understand the function and operation of a half adder, to learn the modeling styles of half adder in VHDL, to synthesize and stimulate half adder. Half adder is a combinational circuit that adds two 1-bit numbers. One of the 2 bit is a carry from the lower stage or a hardwired high or low bit. Symbol and truth table is given. Here sum is equal to a dash dot b plus a dot b dash, carry is equal to a dot b. Next we are going to see modeling styles in data flow and concurrent modeling. This is the VHDL code to synthesize a half adder. Next, behavior modeling. This is the VHDL code. We are going to see structural modeling. For structural modeling, this is the VHDL code to synthesize the half adder. Thank you.